Alrighty, we're going to take a look at here the question number 5 from the 2007 AP exam. And while there's a few tweaks that would have to be made to this question based on our new format, it's still a very good question, and it references the lab that we did in class where we were titrating using potassium permanganate to find the percent hydrogen peroxide in a solution of hydrogen peroxide. But before we did that, we standardized our potassium permanganate using the iron 2 ion. And so using this reaction that we see up here, this balanced redox reaction in acidic solution. And so the first question, or first part of this question says, the mass percent of iron in a soluble iron 2 compound is measured using a titration based on this balanced equation. What is the oxidation number of manganese in the permanganate ion? Alright, so in the permanganate ion, oxygen, of course, always has an oxidation number of -2, unless it's in a peroxide, but this is not. There's 4 of them, so that makes a total of -8. But the ion itself is -1, so we just need to balance the -8 with a +7. So our oxidation number for manganese in the permanganate ion is +7. Now part B said identify the reducing agent in the reaction represented above. And since we got rid of reducing and oxidizing agents in our vocabulary for the new exam since 2014, if they're going to ask this question, they're going to be a little more straightforward and just say identify what is being oxidized. So of course, oxidizing, losing electrons, we're going to want an increase in our oxidation number. And so hopefully you can see iron +2 is becoming iron +3. And so that is the species that is being oxidized, the reducing agent. All right. And so our next part says the mass of a sample of the iron 2 compound is carefully measured before the sample is dissolved in distilled water, and then the solution is acidified with sulfuric acid. So I did the dissolving of the iron compound in the distilled water, and then you got that, and then you acidified it with 10 mils of sulfuric acid. And then we titrated using the permanganate ion until the end point is reached. And so this next question, you are relying on the fact that you remember this lab. Alright, sorry, I'm trying to pause the video. Hold on one sec. The gas was turned on, one of the jets was open. I had to turn it off before I passed out. Sorry. Okay, so this question says, describe the color change that occurs in the flask when the end point of the titration has been reached, and explain why the color is changing. So you had to remember, and of course you were reviewing your labs before the exam, that the iron solution was a pale yellow, and then even when you added the acid it was still pale yellow, and then we stopped this titration when we saw the first hint of pink. And so it changed from colorless, you could say pale yellow, to a faint pink color at the end point. Why is this happening? Because no more of the iron 2 ions are left to reduce the permanganate ion, the manganese in the permanganate ion. And so once that equivalence point is reached, the next little drop of our very, very, very dark purple permanganate solution made the solution turn that nice little pinkish color. Alright, so again, this is one of the labs they expect us to have done, and so they're referencing that lab, and so you're held accountable for remembering what we did. Now part T is a little goofy, but it walks us through the calculations that we did in this lab, but instead of actually using numbers, they want us to use variables, so if they could see how you put this information together. So G is the mass in grams of the iron compound, capital M the molarity of our permanganate solution, V is the volume of the permanganate solution. And so it says using these variables as well as, using these variables, the number of moles of permanganate was M times V, our molarity times volume. Okay, and that's pretty straightforward. So using the variables above plus the molar mass of iron, which they give us 55.85 grams per mole, and the coefficients in our balanced chemical equation, which is at the beginning of this question, write the expression for each of the following quantities. So first, the number of moles of iron. So if you remember, to go between the moles of permanganate and the moles of iron, we had to use our balanced equation of the redox reaction in acidic solution. So our moles of iron, we took the molarity of the permanganate times the volume, which essentially gave us our moles of permanganate, and then that got multiplied by 5 because of our 5-to-1 molar ratio. All right. Now, it would also be accepted if instead of here, you could have said moles of MnO4. Now, I know they said to use those variables, but right up here, they said the moles of MnO4 is M times V, so they would have to accept that. The next thing they want us to define, the mass of iron in the sample in grams. Well, we just calculated the moles of iron. So in order for us to get mass of iron, moles times molar mass. So you could simply say the moles of iron times your 55.85, or if you were in the mode of continuing to use those variables, they would accept M times V times 5, which is what we defined up above, times the 55.85. And then finally, the mass percent of iron. Well, you just calculated the mass of iron, and so then you have to go back and look at our variable list and remember that our little g is representing, here, I'll scroll up for that, little g is representing the mass in grams of the sample of the iron compound. And so to find our overall mass percent, it's the mass of iron that you just gave the equation for, divided by that little g, and then times 100 is how we get a mass percent. Again, if you were in super variable mode, they would also accept M times V times 5, which was our moles of iron, times 55.85, which then makes our mass of iron that you see used in this expression, divided by G times 100. So either of those are acceptable, either of those expressions. Our last question is what they typically like to talk to us about. What happens if, okay? And so what effect will adding too much of the titrant have on our experimentally determined value of the mass percent of iron? And justify your answer. So basically, if you were titrating, instead of stopping at the slightest sign of pink, you went a little too far and it turned a very dark pink color. So essentially, you added a larger volume of your permanganate than you needed. And so the trickle-down effect would end up being that the mass percent of iron would be too large. Why? Because your volume added would be too large, which we then use to calculate moles and moles of iron, so that would be too large, as well as the mass of the iron, and then ultimately the mass percent. So you would have a trickle-down effect of the because you started with too much of your volume of titrant. All right. So I'm going to piggyback our last question now with the question from 2014, number 3, with our good friend the galvanic cell. We did a lot of this in one of our tests already, so I'm just going to zip through this. But here you see a standard galvanic cell. I've got a strip of copper immersed in copper nitrate solution. Sorry. Come on. And then I've got a strip of zinc immersed in some, tin, immersed in some tin nitrate solution. Okay, and we've got our salt bridge with potassium nitrate. So there's our picture. So the first question says, student is given a standard cell, copper electrode, tin electrode. As the current flows, the student determines that the copper electrode is increasing in mass and the tin electrode is decreasing in mass. And so we need to identify the electrode where oxidation is occurring, explain your reasoning, and then as the mass of tin is decreasing, where is it going? And so here we see that tin is the anode. That's where the oxidation is occurring. The tin electrode is losing mass, and our anode is always the one that is losing mass. So where is that mass going? Tin atoms are oxidizing and becoming tin ions in solution. So there's a flow of mass from the metal into the solution. All right, so you want to make sure you reference both the solid atoms and the ions so we know that the mass is flowing into the solution from the metal. And then it says, in the expanded view of the center portion of the salt bridge, draw and label a particle view of what's occurring. Now, it doesn't say anything about justifying, so you don't have to do anything more than just know that your positive ions always flow towards the cathode because the positive ions are leaving the solution, and your negative ions always flow towards the anode because the positive ions are entering into the solution. So we have to balance those charges. So our potassium would go to the left towards the cathode, and our nitrate would go to the right towards the anode. And again, it just wanted the picture. No explanation was needed here. Next it says that a non-standard cell is made by replacing 1 molar with 0.5 molar solutions. Volumes are the same. Is the cell potential of our non-standard cell greater than, less than, or equal to the standard? And justify your answer. Well, since they're both dropping down to the same amount, our cell potential is not going to change. Q is the same. Okay, Q is still equal to 1. Q value is the same. And so you could reference the Nernst equation here. You could even do a calculation if you wanted. But our cell potential would not change because our concentrations are still equal. If the concentrations were different, then we would have a change in our voltage. So if our tin concentration increased, okay, then our Q would be bigger, which means, of course, that we'd have more product, so our cell voltage would be lower. If copper increased, then our Q value would be smaller, which means we have more reactants, and our cell voltage would be larger. But since Q is staying the same as 1, our non-standard and standard cells would have the same potential. But if we use these cells to power an electronic device or a light bulb or something, who's going to last a longer time? And now we would see that the cell that's made with the 1 molar solutions would have our standard cell. It would be able to run longer because there's a larger supply of copper ions that are available for that cell to run longer. So the non-standard would run for a shorter time. The standard would run for a longer time. And of course, they both would run until we reach equilibrium. And when we reach equilibrium for a voltaic galvanic cell, E is equal to 0. The cell dies. All right. The last part of this question says, in another experiment, student places a new tin electrode into a solution of copper nitrate. You're like, whoa, what's going on? But this is just like an activity series lab. You're just trying to put this in and look at the plating and see if the copper plates onto the tin, etc. But just follow the question. It says, using information from the above table, write a net ionic equation for the reaction between the tin electrode and the copper nitrate solution that would be thermodynamically favored. Justify that the reaction is thermodynamically favored. So the copper 2 ions plus the tin solid, the E value is positive. It would be a 0.48 voltage. Therefore, it's thermodynamically favored. That's all you would have to say about it. Okay, so you're looking at the combination of these E naught values that would give you a positive voltage. And how do you know it's copper plus 2 and tin plus 2? Because in our previous picture we saw that the copper 2 nitrate and tin 2 nitrate solutions. And so that's how you know. This is going to run out really quick, but for the calculating delta G, plug and chug into NFE. There's 2 moles of electrons exchanged, and do make sure that your delta G is going to come out in joules, and if you want to switch it to kilojoules, divide by 1,000.